In the last video, we saw that we can go from Lagrangian to Hamiltonian through a Legendre transformation. So I start from L of Q, Q dot and T, and I go to Hamiltonian, which is a function of Q, P and T. Okay, and as you may recall, I was saying that we are going to treat Q and P at equal footing. And when we went from L to H, we had the following relations which were true. One is delta L over delta T is same as delta H over delta T. So the partial derivatives of L and T with respect to time are equal. Okay, and also if you take the the derivative of L with respect to one of the coordinates, then it is same as the derivative of the Hamiltonian with respect to the same coordinate, except for a minus sign. So these two are identical. And also we had Q dot to be equal to the derivative of Hamiltonian with respect to the corresponding momentum, conjugate momentum. Okay. Remember, the P turned out to be the conjugate momentum, okay, that you had seen earlier. Okay, so this is what these three you have, these equalities you have purely arising from you going from L to H through Legendre transformations. Okay, they do not, you didn't use equations of motion for these to hold true. Okay, so if you also further demand that the coordinate Q satisfies the Euler-Lagrange equations of motion, from that you can arrive at the following equation of motion, which was the following. So if you look at P, maybe not here, P, if you look at the time derivative of one of the momenta, let's say Pk, then that was same as delta H over delta Qk, and there has to be a minus sign here. So whenever you are taking the derivative of H with respect to Qk, not whenever, I mean in these equations of motion, there is a minus sign. And we also said that because you are treating Q and P at the equal footing, we will also treat this one as equation of motion. Okay, but remember this one you didn't arrive at by using any Euler-Lagrange equations of motion, but in the Hamiltonian formalism we are going to treat this at the equal footing to this one. So delta H over delta Pk, and these are your Hamilton's equations of motion. Okay, that's fine. Now let's ask, what is the total derivative of Hamiltonian with respect to time? So I am asking, what is dH over dt? And it's easy to evaluate. dH over dt is delta H over delta Q, and then you have dq over dt, which is Q dot, and Q dot is delta H over delta P. Delta P. Okay, let me put a K, and that's fine. So there's a summation over K implied here, plus I will take a derivative of delta H over delta P, okay, because H is also a function of P, and there are several of them, so let me call it Pk, and sum over all the Ks. And then you have a Pk dot here, but Pk dot is minus delta H over delta Qk, so I put a minus here, delta H over delta Qk, and then the third term will be the partial derivative of H with respect to time, because your Hamiltonian could in principle depend explicitly on time. But now these two terms are equal. You have delta H over delta Pk, delta H over delta Pk here, delta H over delta Qk, and delta H over delta Qk. So these two cancel. Okay, so let me just cancel them. and what you're left with is delta H over delta T. So the result we get is the total derivative of Hamiltonian with respect to time equals the partial derivative of Hamiltonian with respect to the time. Okay, that's nice, and it's a nice result. You can say more because you also know that the partial derivative of h with respect to time is equal to delta L over delta t. Now, if your Lagrangian didn't depend explicitly on time, then your Hamiltonian will also not depend explicitly on time. That is what this equation is saying. Okay, so let's say the explicit time dependence is not there, and if that is the case, then your total time derivative of h will be 0. So if L or equivalently h does not depend explicitly on time, then this thing is 0, and if that is the case, then dh over dt is equal to 0, which means that Hamiltonian is conserved for such system. Is conserved for such systems. Okay, and you may also recall that very early in this course we had encountered this quantity pq dot minus L, which is what we are calling Hamiltonian here, and this is what we call Jacobi's integral in very early lectures. Okay, and we also saw that this quantity can be identified with total energy if certain conditions are met. Okay, it's not always the total energy, but under certain conditions it can be identified with total energy, and let me just remind you what those conditions were. Okay, you can go back to those early lectures and see. Remember that we showed, I think we were calling it small h at that point of time, but this small h, and let's call it capital H now, but at that time it was being written as qq dot nt, not as qpt. Okay, and we saw that this is T2 plus U minus T naught. Okay, where the kinetic energy T you can write as T2 plus T1 plus T naught, and the terms T1 and T naught are present only if your transformation to generalized coordinates involves time explicitly. Okay, I hope you recall this, and if that is the case, if they are explicitly time dependent transformations, then you have T0 and T1 as non-zero quantities, and this is what you get here then for the Hamiltonian. Okay, and here U is a function of Q only, the coordinates only. Okay, but let's suppose that the kinetic energy T only equals to the quadratic piece, so it has Q dot square, okay, qk dot ql dot contracted with some ai akal. Okay, only if this piece is there, and if u is only a function of the coordinates, not of the velocities, then our h becomes T2 plus u, and we saw that this is what was equal to the total energy. Of the system. Okay, so let's say you have such a system where the Hamiltonian can be identified with total energy, and then the above relation dH over dt is equal to 0, if that holds true, would imply that total energy is conserved. Okay. Let's take a quick simple example of a harmonic oscillator. And if you recall, the Lagrangian is simply half mx dot square minus half k square x square. Okay. Okay. So if you now do a Legendre transformation, then you know that the Hamiltonian will be px dot, pq dot is your px dot minus, and then you have your Lagrangian, which is half mx dot square minus half. Okay. And you also recall that your del L over del X dot is what is P, okay, which if you take the derivative, you get mx dot, okay, which you can solve to write x dot to be P over m. And your kx square, I think there is no square here. Okay, so that is fine. And where were we? Yeah. So with this, I can write the Hamiltonian to be p square over 2m. Okay, I'm just substituting for x dot p over m. So I get p square over 2m plus half kx square. Okay, so that's the Hamiltonian, and which you already knew because this is the total energy for this system. And the system is conservative. It depends only, the potential energy depends only on Q, only on the X. And this is anyway just has the quadratic piece in velocities. So you expect that the Hamiltonian will come out to be this. And because this Lagrangian does not depend explicitly on time, remember the coordinates depend on t, but that time dependence is implicit through the coordinates, but there is no explicit time dependence in here. So partial derivative of h with respect to t is vanishing, and which implies that the total derivative will also vanish with time. Okay, which is just that the total energy is conserved, which you already know for a harmonic oscillator, which means that your h will be a constant. Okay, so let's call it E, that constant energy, and which implies that these pieces p square over 2m plus half k x square, they will be equal to some constant E. And if I divide by energy on both sides, I get this. Okay, that's good. Now we can ask how things look like in phase space. Okay, you remember we introduced phase space. Let me go back. This was the 2n dimensional space in which you have the axis to be q1, q2, so and so forth, and p1, p2, and so forth. Okay, so for a harmonic oscillator, one dimensional harmonic oscillator, which we have just looked at, the phase space is how many dimensions? Phase space is 2-dimensional, right? One for Q and one P. So you have your let's say here. Q and P, or maybe I think I called X and P, so let me write X. Okay, now we have the equation as P square over 2me plus K over 2e x square is equal to 1, right? That's what I think we had. Yeah. Now if you are given one oscillator, okay, and then for that oscillator this is the condition that has to be satisfied. So if you look at what this represents, it represents an ellipse in the xp plane, but for simplicity let me put all the constants m and k to be 1. Okay, then you just have circles. So you have p square plus x square is equal to 2e, right? So you get concentric circles, and the radius of the circle depends on your total energy of the system. Okay, treat them as circles. These are not very circular things which I am drawing. Let me draw again. So you have one circle here, which this corresponds to some energy. This corresponds to a little higher energy. Okay, so your system, depending on how much total initial energy has been given to it, it will be moving along one of these circles. Okay, so your entire system is denoted by one point. At a given time it will be somewhere, and as time changes that point is going to move. Okay, I hope that is clear, because if you specify the coordinates at a given time, all the coordinates, in this case it is only one, and all the momenta, and then that represents one point in your 2n dimensional space. Okay, so your system is going to be represented by a single point in phase space. Let me write this down anyway. So system at any time t will be represented by a point in the phase space. Right, that's clear. So now as time changes, that point is going to move with time, so that point is going to flow. Okay, and what I have drawn here as these circles is that if your energy is such that your point is here, then it's going to move along this circle for this one dimensional harmonic oscillator, and if your energy was different and it was such that it is here, then it's going to move on this circle. Okay, so that's what our the phase space will look like. The trajectories of this point or the system will look like in the phase space. Okay, that's good. Now I'm going to prove a very nice theorem, and the theorem is the following. Actually, before I say the theorem, let's ask the following. So let's say I have some, let's say we are given a system with 2n dimensional phase space. Okay, meaning it has n generalized coordinates and correspondingly n generalized momenta, and the particle and the system will be denoted by a point in that phase space, by a point in the phase space. So I do not wish to draw, I mean I cannot, not that I wish, but I cannot draw a 2n dimensional space, but I can draw a 2-dimensional space. So I'm going to draw it like this. So you can imagine that Q stands for all these coordinates. You can think that this is a 2n dimensional space. Okay, so you have all Q1, Q2 and Qn in here perpendicular to all these, and similarly P1, P2 and so forth. All these coordinates are here. And imagine a patch, a region. So a region, not a patch, because I'm thinking of 2n dimensions. So imagine a region, okay, here, and this is going to occupy some volume. Okay, so just to give it a little bit of 3-dimensional look or whatever, let me draw this curly line. So you imagine it encloses some volume. Okay, so right now I'm not trying to even make any connection with system or whatever. Your system is given. Okay, so each point corresponds to one system, but forget about all that how many systems are there and all these questions. Just look this as a geometrical problem. We are given some volume enclosed by this. Okay, so the region, let's call it, I think I want to call it some R or something, whatever. Okay, and we also tell the equations of motion. So each point here, okay, is going to evolve in time according to the Hamilton's equations of motion. So it's going to go somewhere as time goes on. And what we want to ask is, if I start with some volume here, so if I look at all these points are going to move in time and go to somewhere else. And I want to ask how this volume is going to change with time. Okay, so if I wait for some time, and after a while, if this initial volume enclosed here was V0 or V at time 0, T0, what it becomes after some time has passed. Okay, that's what we want to ask. Yeah, let's say it becomes like this. Okay, so I'm not saying the shape will be similar or same, shape changes, and we want to know whether it has increased or decreased or what has happened. Okay, at a different time t. So you go from t0 to t, and this is what we want to ask. Okay, and what we are really looking at now is what is called Liouville's theorem. I will tell you at the end what the theorem is. VILLES Liouville's theorem. Okay, so I hope the question is clear, and let me just create some notation. So I want to define this entire set of coordinates q1, q2, so and so forth, qn, and then you have p1, p2, that's pn, so you have all the 2n coordinates here. Let me call these collectively as x. Okay, and I put a vector as x just to mean all these that it is a multi-component thing. Okay, and then also I have my Hamilton's equations, which let me write down. Qk dot is delta h over delta pk, and you have pk dot as delta h over delta qk, and if I am differentiating h with q, I remember that there is a minus sign here. Okay, so I define a vector f to be the following. So delta h over delta p1, delta h over delta p2, so and so forth, delta h over delta pn, then you have delta h over delta q1 with a minus sign. So what I'm doing is I'm just listing these right hand side parts here and here along this. Okay, and you go further, and delta h over delta qn, again there's a minus sign I put here. And this entire set of quantities I denote by vector f. Okay, so this equations of motion, Hamilton's equations of motion here, using the notation which we have written down just now, can be written as x dot is equal to delta f over, is equal to f. Right. So if I look at, for example, what is x1 dot, it will be f1, which is delta h over delta p1. And what is x1? It is q1. So q1 dot should be delta h over delta p1, which is correct, which is what you have it here. And let's look at this one. This is, let's say x of n plus 1. F or x of n plus 1 would be p1, and p1 dot should be f of n plus 1, which is minus delta h over delta q1, which is correct. Okay, so all I have done is written down Hamilton's equation in this form. Beyond that I have not done. There is no content in here, it's just notation. So these are our 2 and first order differential equations in time. Okay, and then I can write x at any time, at time t0 plus dt. So I'm starting with time t0 and I look at what happens after a small interval of time dt, and you can write down this as x of t0 plus f of x at t0 times that small time interval dt, and then you will have all the higher order corrections. Right, this is just this equation written or solved near t0. Okay, that's fine, that's good. So what is contained in here is the information about how the points are going to move in time. Okay, that is what is contained in here, which is same as this equation. Now let's first, before we are able to ask how the volume is going to change with time, I should first write down the expression of the volume and write down how volume changes. Okay, so the volume is the following. So let me write down here itself. So volume at volume at t0 is what? Is d2n x at t0. Okay, which is nothing but dx1, I'm dropping the t0 now, dx2, so and so forth, dx2n, which is just dq1, dq2 up to dqn, and then dp1, dp2 up to dpn. Okay, that's what the volume is at time t0. Okay, you can put t0 here as the arguments. And then at time t naught plus dt, you will have d2n x of t naught plus dt. Okay, which is again the same thing. Okay, similar thing, dx2n t naught plus dt. Okay, so that is fine. That was easy. Now how are the two volumes related? This one and this one. You know how they are related, and the relation is this. You take you go let me just show here. You see the x is going to change like this. So you have a transformation of your x from this to this one, which is given by this relation. Okay, so all you have to do is find the Jacobian of transformation, right? So all you have to do is find the Jacobian, and let's denote Jacobian by J. Then you know that the two volumes are related by the following: dx2n at t0 plus dt is equal to dx2n at t0, and the change is this. Okay, it's you have a factor of the Jacobian which comes in here, and if you recall, where the Jacobian is just the determinant of this matrix dx k t0 plus dt, okay, over dx m, let me put m here. Okay, so you have to just take these you have to construct the matrix which contains all these partial derivatives. So, and k runs from 1 to 2n, m also runs from 1 to 2n. So this is 2n cross 2n dimensional matrix, and you have to find the determinant of this and then multiply it here, which gives you the new volume. Okay, so now the task is to evaluate that Jacobian. The moment I know the Jacobian, I know the answer. Okay, and I will have to just integrate over that entire region to generate the volume. Right now these are differential elements of the volume. So let me do that. Let me try to evaluate the Jacobian, and of course to do that you have to use this piece of information that which knows how things are changing with time. So let me write this equation here, this vector equation x as x t0 plus f times dt in the component form. So in component form, you have x of k t0 plus dt is equal to x of k at t0 plus f of k x at t0 dt, and you have higher order terms also, which anyway we are going to drop because we are looking at infinitesimal dt. I can drop it here itself, it's unnecessary to carry this. Okay, so let us calculate this derivative, delta xk or delta xm. Del xk over del xm at t0. Okay, clearly this will give you delta km. Okay, unless k is equal to m, this guy is 0. Only when k and m are equal, this is going to give you 1, plus the derivative of f with respect to xm. So delta fk over delta xm. I will drop this x of t0 for ease of writing, okay, and clarity, but it is there, that argument is there, and you have a dt here. Okay, let me keep writing this. Now what you have, if I want to write the same thing using matrix notation, then the right hand side, this side, you can write as identity matrix plus, let me I think I want to put dt here. Yeah, that's correct. Let me denote this matrix by matrix A. Okay, so the matrix A has as its components delta fk over delta xm times dt you have, and you have other order dt square terms. Okay, so what we want to do is look at the determinant of this, right? So we are interested in finding out the determinant of 1 plus a dt, and we want the result only up to dt, and we are not interested in higher order contributions. Now that's easy actually, that's not very difficult. All you need to do is, and there are many ways in which you can do this, but you can use the following formula which you should be familiar with. Let's say you have A as a matrix, then the determinant of that matrix can be written as epsilon I1, where epsilon is Levi-Civita tensor. Let me be a little bit more clear. Epsilon I1, I2, In times A I1 1, A I1 I2 2, A I N N. Okay, so that is the result, and you know the Levi-Civita tensor is, or this totally antisymmetric matrix is 1 if you have this is, so epsilon 1 2 3 so on and so forth, n is defined to be plus 1, and whenever you interchange any two indices you pick up a minus sign. Okay, that's how this epsilon is defined. And ai11, these are the matrix elements of the matrix A. Okay, so that's what I'm going to use here. So let's see what my Jacobian is now. My J is epsilon I1 I2, and it will go up to 2n because you have a 2n dimensional 2n cross 2n dimensional matrix. And then here you have your 1 plus A dt, right? So in component form this becomes A1, the first, sorry, corresponding to this you have to write delta I1 1 plus capital A I1 1 dt, right? That's what you'll have here. And then you have all those factors, and for this last one you will have delta I2n 2n plus A I 2n 2n dt. Okay, now let's collect terms of order, I mean the terms which are not proportional to dt, and then the terms which are proportional to dt, and then we will drop the terms which are higher powers in dt. Okay, that's what I'm going to do. So the terms which do not involve L in dt are going to come from multiplying this epsilon with the deltas, okay, without involving any of the a's. So if you have this epsilon multiplying all the deltas, these deltas will force the this delta will force the I1 to be 1 in here, so it will become epsilon 1. Then I2 will be forced to 2, so it will become epsilon 1 2, and similarly this thing will be force I2n to be 2n. So one term you are going to get is epsilon 1 2n so forth up to 2n. Okay, so that's the term without any dt. Plus, now you are going to generate the terms proportional to dt in many ways. So if you pick up this factor from this term and all the others are deltas, then you are going to have a term proportional to dt. Similarly, if you pick from this one a delta and you pick A21, A2, AI2, 2 and all others to be deltas, then you get another term which is proportional to dt. So let me write that down. So you are going to generate terms like this. Okay, let's reduce some labor in writing. Okay, so you are going to get AI1 t, sorry, AI1 1 dt, and all the others will be just deltas, right? So you'll have delta, I'm just writing delta I1 1 also, but it is not there. I will just strike it off. I2 2, and similarly you proceed and go up to I2n 2n. Okay, and this factor is missing in this one. And these kind of terms, let me, if I was a bit more careful, I could have, yeah. So I'll just pull out this term, because you see now, you understand, you are going to, the next term which I'm going to write will again have an epsilon. It will have a corresponding a times dt, and the same pace with this being removed, and you'll keep this. Maybe let me, okay, let me write down plus epsilon I1 I2n, and then you will have a I 2 n 2n dt and all these deltas. I subscript 2n 2n. So this time, in the last term, this will be gone, and all the other terms that you are going to generate will involve multiplication of at least 2 pieces of a's, which will bring with them at least a second power of dt. So we are going to drop all those. So this is not there. Okay, so all those other terms will be higher orders in the change in time. And now that is easy. Your first term is just 1, which you also expect, because to the lowest order there is no change, right? Because the time you are looking at the volume change after an infinitesimal time, so you expect that Jacobian would be to the lowest order 1. So that's correct, that's good. You have got to the 1 here, plus you expect something proportional to dt. Okay, and let's look at here. All these deltas will force all the, except for I1, all the other indices to be equal to what you have here. So you will have epsilon I1 2 3 4 up to 2n, and then you have ai11 dt. Correct? Yeah. So you will get, let me write down epsilon I1 1 2, sorry, not 2 2 3 so forth to 2n. Okay, with ai 1 1 dt, and all such terms are here. Let me write down anyway. Epsilon, this will be 1 2 so forth up to 2n minus 1, and then you will have I subscript 2n, and you will have a I 2n 2n dt. Okay, plus higher order terms. Now see, if this will be non-zero only if I1 is 1. If I1 is 2 or 3 or something, it's going to be 0, and you have a summation over I1 because its summation convention is still here. So the only possibility for this is to be 1, and that will give you a positive sign, because this will be fine, epsilon 1 to 3, and that will force this one to be a11. So it is 1 plus, this will be a11 dt, next one will be a22 dt, and similarly a2n 2n dt. So you have trace of a times dt. Okay, the sum of all the diagonal entries is the trace of this matrix A. Okay, that's good. Now this is just 1 plus, let me write down. Now you remember your capital A was the matrix, this matrix. Now we are looking at the trace of this. So you have delta fk over delta xk, and you have summation over k, which is just gradient of, divergence of f, right? So I can write as divergence of f. Remember, divergence is del f by del x1 plus del f by del x2, which is just what is appearing as trace for you here. And dt is still there, plus higher order. Okay, so we are almost there we have shown that if you look at a differential volume element in this 2n dimensional space, sorry, T naught plus dt, then it becomes 1 plus divergence of f dt. Okay, I'm going to drop now all the higher order pieces. Okay, that is how it transforms. So that's what your Jacobian is. This is your Jacobian. Now let's look at the volume. So volume at T naught plus dt, okay, is just obtained by integrating all the differential volume element. Okay, and this, as we have determined, is just d2x and then d2nx at T naught, and then you have your Jacobian, which is 1 plus divergence of f times dt. Okay, so let me split it into two integrals. So one will have this 1 multiplied in here, and this will give you the volume at time T naught. Let me take it to the left hand side. Okay, it will have a minus sign then, and then the second term will be proportional to dt. So if I divide by the time dt, I should have written delta t, it would have made more sense. So anyhow, so you have let me call it to make it look more appropriate. Okay, so that is what I have. So instead of dt, let's put delta t and then put delta t to the left and take that limit. Okay, then this will be only this piece remains here. So you have the integral over the volume element of divergence of f, right? So dv over dt evaluated at time t equal to T naught is integral divergence of f times d2nx t0. Okay, now if so happens that your f, which you defined here, where is it? Yes, this f, okay, which are on the right hand side of your differential equation, then yeah, if it so happens that the f which you have here is divergenceless, so let's say I assume that divergence of f is equal to 0. If that is true, then dv over dt at any time t naught will be 0, right? Or at equivalently at all times t naught, at all times will be 0. So the volume is not going to change with time if your f was divergenceless. So that is the generic conclusion for any system of ordinary differential equations. But now let's look at what we have for our specific case of Hamilton's equation. So let's see what we have for divergence of f. So divergence of f for Hamilton's equations. Let's see. So your divergence of S is, let's recall, delta by delta q1, that's first coordinate, and then recall what f was. F was your, where is it, delta h over delta p1. Okay, let's write it here. Okay, similarly you keep on going up to qn, and you have delta h over delta pn. Then you have more terms, delta over delta p1, and let's recall what fn plus 1 was. Fn plus 1 was minus delta h over delta q1. So you have, instead of a plus here, a minus delta h over delta q1, and then you continue the P n and delta H over delta Qn. Okay, that's all you have. So this is H is being differentiated with respect to Q1 and P1, and here also the same thing, and the order does not matter, and there's a relative sign, so these two will give you 0. Similarly, all the other terms will also cancel pairwise and will leave you 0. So indeed, for our Hamilton's equation, we have divergence equal to 0, which means that whatever volume you take in the phase space, it's going to evolve with time in such a manner that this time derivative is 0, meaning the volume is going to remain unchanged. Remains unchanged with time. Okay. The shape of the volume may change. It will change in general, but the volume contained or all the points which move the volume which they are going to span out, it will still be the same as the original volume. Okay, and this is what is Liouville's theorem. Okay, that's a nice theorem which is very useful in statistical mechanics when you talk about different ensembles. But here we will not even worry about defining an ensemble. There is no need in here, but this is a very useful theorem which you will use, for example, in statistical mechanics. Okay, I think this is all that I wanted to say here. I note that, yeah, I can make a quick remark. I hope this this is clear that this is the total time derivative of volume. Okay, and you should contrast it with the partial time derivative. Okay, this statement where the partial time derivative is 0 is different from the total time derivative. Okay, so when you're talking about a total time derivative, in addition to time changing, the coordinates are also changing, right? Because d over dt is partial derivative with time plus derivatives with respect to all the other coordinates. So you are really moving together with all those points as they move, and you are then asking about the volume, whether it changes or not. But if you are just looking at this partial derivative, then you are staying put at one place and you are just looking at the time changing, okay, as time passes, and then of course the volume will be changing there. It will be reducing, for example. Okay, so what happens there locally is different from what happens when you are flowing with the points. So we are talking about this piece. We are not talking about just time passing at the same place. Okay, anyhow, so this is the Liouville's theorem, which is quite useful, and let's meet in the next video to carry this this subject further.